Okay, so 721ers, just listen up. Really what we've done up till now has been preliminary stuff, so it's been all the skills that you need to do the two assignments. Where we are now, I want you to finish the amplifier on breadboard. I don't think anyone's still working on that, so that's that ticked off. Show the PCB design of the amplifier to the demonstrators, in other words myself and Mike. Build the surface mount board in the soldering room. Probably 2/3 of you have done that. Some people are still in there now, doing it now. Test surface mount board, so plug it into your phone, make sure that that audio amplifier works properly. Okay? So I want everyone to complete that by the end of this week, by 12 o'clock today. Okay, we draw a line under that because the thing we want to go on to then is, of course, to start work on this idea of the photopopper. Now, I've got one over there that I built using a microcontroller. Three of the guys over there have got them working already. What is a photopopper? What's the concept of a photopopper? Well, what it is it's a little robot in its extreme form, because they're also known as solar bots. What you have is a quite interesting situation, because you have a solar panel. You've got a solar panel that you expose to light, but the amount of energy which is coming off the solar panel isn't enough to run an electric motor. It's just not enough instantaneous power to be able to run this motor, which is the other side here. So what a photopopper does, or what a solar bot does, is it says, okay, I recognise that I don't have enough power to drive the wheel around and drive it across the table. Guys, you're not in the class. You're not in the class. If you're not in the class, you can stay here, but please be quiet while you're in here. So you've got the photopopper. This circuit here will not run on its own. So what we want to do is we want to put something in the way, which is a box, which instead of trying to run the motor all the time, runs it periodically. So every now and then, it just fires it just for a second or so, and then it's going to go back to sleep and accumulate again. Okay, so the analogy of that is buying a big object from a small wage. So the one example I used before, most people in here can't afford to buy a Ferrari. But if they saved up for 10 years or whatever, they probably could buy a Ferrari, right? So what you have inside here is this concept of the energy's coming in, so here's your storage. And say, for example, we can run the motor at this point here. And this is the vessel we're filling up with virtual electricity. So when we reach this point here, the motor can run. Right? Below this it can't. Well, the direct analogy of this storage thing is a capacitor. So in other words, what I want to do is I want to accumulate the energy from the solar panel until I reach a particular voltage threshold, at which point I know I can run the motor. Now, what a capacitor looks like when it's charging is something like this. And this point here is going to be your V in, which you can get because we'll give you a solar panel. On that solar panel, when you measure the open circuit voltage, so you can do it here, it's not going to be much here, it'll probably be about 2 volts here. You do it under that light over there, you'll probably get 4 or 5 volts over those panels. But your open circuit voltage, you can't go above your open circuit voltage because you can't just pull energy out of the air, you can only have what's available. So that point there, V in, is your open circuit voltage for the solar panel. And let's say, for the sake of argument, this is 4 volts here. Okay? So the solar panel is slowly charging this capacitor. So let's just redraw that slightly now. So the situation we have is there's our solar panel, and it's going off how should we draw this? Let's just draw a capacitor like this. So it's going off and it's charging up that storage capacitor. Once that storage capacitor is charged to the open circuit voltage, in this case 4 volts, it's not going to charge anymore. You can leave the solar panel connected for 100 years. You'll only ever get the open circuit voltage or less inside that capacitor. What the photopopper does is the photopopper says, well, I can only ever reach 4, but why don't I at say 3.5 volts? So this would be my turn on point. So turn on, and when I drop to say 2.5 volts, I'm going to turn off. So in other words, I'm putting energy into my savings bank, and as soon as my savings bank reaches a point that I'm happy with, I go out and buy me Ferrari. And there I empty the bank. Well, I don't empty the bank because we don't really want to do that, but we'll go from, say, 3.5 volts to 2.5 volts. And then the whole cycle carries on again. So what happens when we look at the motor, so we've got the motor here, standard symbol for a motor. As far as the motor is concerned, if this is time, we would like it, the motor, to just run continuously over all time, because then the robot will just wander across the floor, which is what we want. But we can't do that because we don't have enough energy. So what we do is this. So by adopting this strategy here where this is turn on here and this is turn off here, what we end up with is the motor doing this. So it's on for very short periods of time, but it's better than not running at all. So what it means is that little solar box now sits on the table and periodically just, and then it takes a long time to charge again. Now here's one that Mike built last year, which he familiarly named Blue Bot, and quite an advanced little piece of kit this. You want to just have a look down onto that? So this little device here has a storage capacitor, or 2 storage capacitors here, and a bit of energy management inside here, 2 motors that it's driving, and it also had a radio link on it, so it had a Bluetooth link so you could see what it was doing on a mobile phone as well. Now we're using quite a big panel here. That doesn't look like a solar panel, but that's actually what's underneath the glass and the solar panels. Unfortunately it's become broken, so we can't run this one, but that's quite an advanced little piece of kit, that. Quite nice. Okay, so you've got a motor that periodically fires. That one uses a microcontroller, a computer, to run that. Now the examples that we see over here, or I'll show you in a second on the board, don't have that facility. Okay, all they are is you've got a measuring device. As soon as you go up to the point where you've got enough energy to drive the motors, it fires. It turns on a transistor usually that's then going to send a high current out to the motor, and the motor's going to rotate. So in other words, we can do some work. Now previously we couldn't do any work, because if we just took the solar panel and connected it directly to the motor, no work was done because the motor didn't go round, right? So this is actually a lot better than just sitting there and consuming the energy coming from the panel in heat in the motor without actually driving it round. Okay, now, so say for example you've got a circuit which you're testing. We've got 1 or 2 ways you can test it. We've got a very, very bright light over there, which is running my Photopopper, because I built one using an AT-Tiny85 microcontroller over there. You're welcome to look at, but that electric motor is firing fairly regularly over there. You're familiar with current sources, I hope. And what you have is you have a situation where you have a current source, but the current source is limited in what it can drive. That's pretty much a model of what the solar panel is doing. It provides current, and it has a peak voltage attached to it, which we're saying in this case is about 4 volts. Might be, depends how much light it gets, but I'd say typically 50 milliamps, something like that might be typical. Now, rather than keep using the light over there and moving all of your stuff over there, something that's probably more sensible to do is just to use the DC power supply. The DC, let's just not complicate things, let's just draw a square for that, so we can have a DC power supply. Now if I connect a DC power supply to a, say, a 1 farad capacitor, how long does it take to charge that capacitor? So I take the power supply here and I connect it onto the capacitor. How long does it take to charge the capacitor? Hmm? Well, it does, but slow, medium or fast? Well, if I just gave you those 3 categories, slow, medium or fast, and I connect a capacitor across the output of, say, a 12 volt power supply, do you think it will charge that capacitor? Well, will it take an hour? Will it take a minute? Will it take a second?
A few seconds, depending on
Yeah, it's of the order of seconds. Well, it's probably nearly instant, I would imagine. The 1 farad capacitor on there I'd charge in a second or less, I would have thought. Now the reason for that is that power supply can supply huge amounts of current. Your solar panel can't. Your solar panel on a good day might give you 150 milliamps, something like that. Now I said that we don't want to keep using the solar panel over there. The bot is driven by the solar panel, but it would be nice if we could model what was going on these devices here. Well, we can turn down the current, that's one way we can do it, of course. But the other way that we can do it is we can just say, right, we've got DC power here, let's put a resistor in the way, and let's restrict the current which can flow in our circuit. So in other words, if this resistor here can be changed, you can simulate different amounts of sunlight coming from the solar panel without using the solar panel. In other words, you can test your circuit. So now it goes into the capacitor, you turn on the power, and rather than it charge this in less than a second, it's going to charge